We're continuing our study of logic in section 3.3 on the conditional and biconditional. Back in section 3.1, we learned that truth tables are used to list every possible way that a simple or compound statement can be true or false. The next of the 5 basic truth tables that we're developing, this will be number 4, is called the conditional, sometimes called the if-then. The truth table for the if-then has only one case where the result is false, and that is if the P is true and the Q is false. This is probably the hardest one to remember, but it's the only false case for the conditional. T is true, F is false. T implies false is false. All of the other cases are true. So even though it's probably the hardest to remember, you have to focus on the one false case and just remember that the others are true. You might say this in words: a conditional is false only when the antecedent, sometimes that P is called the antecedent, is true and the consequent is false. Antecedent is the P and consequent is the Q. For example, if I gave you the statement, "If you need help, then I will help you," this compound statement is false only if the antecedent is true and the consequent is false. If you need help, then I will help you. You need help is false. I will help you is true, produces a false compound statement here. It's the only case where it's false. Now we're up to 4 of the 5 basic truth tables we will need to complete our study of logic. We started out with the conjunction and disjunction in section 2. We added the negation. Now we're adding the conditional. The 5th one is called the biconditional. Notice that the conditional is an arrow pointing to the right. The biconditional symbol is an arrow pointing in both directions, or a double-headed arrow. The biconditional is only true when P and Q have the same truth values. In other words, they're both true or they're both false. So if you look at the truth table for the biconditional, it's only true if you get P true, Q true, or if you get P false, Q false. Otherwise, it's false. That gives us all 5 of our basic truth tables. This is sort of a visual summary with the memory aids below them. We've got the 5 truth tables. Rather than memorizing them line by line, my suggestion is to learn the memory aids or create your own memory aids so that you can remember what these tables result in without having to memorize them line by line. For the negation, I would say the memory aid is T changes to F, F changes to T, or you might say the negation changes the truth values to their opposites. However you want to phrase that memory aid so that you can remember it. For the and, the memory aid is it's only true if they're both true. For the or, the memory aid is it's only false if they're both false. For the implication or the if-then, it's only false if P is true and F is false. To me, that's the hardest one to remember. And finally, the biconditional, it's only true if P and Q match. However you want to rephrase those memory aids, there are 5 of them, and you need to be able to say them to yourself so that you can produce those tables if you need to. I referred to some of our work as working in the interpretation mode. These are your tools for working in the interpretation mode. Now let's see if we can take some more complex logical statements and apply what we've learned here to those statements. Sometimes we actually need to leave interpretation mode and move to translation mode, and this is when we need to translate from logical statements to English statements or vice versa. So let's practice that a little bit. Recall that statements of the form P implies Q are called conditional statements. Again, the implication, the arrow pointing to the right, has various names. Sometimes you call them if-then, you can call it an implication, you can call them conditionals. Conditional statements can be written in the form if P then Q. Sometimes the word then is left out. If P, comma, Q. It just means that in English language sometimes you leave out the word then, but it's understood to be there. For instance, all the following are conditional statements. If we order pizza, then we can have it delivered. If you go to the movie, you will not be able to meet us for dinner. If n is a prime number greater than 2, then n is an odd number. You don't actually have to have the word then in there for it to be understood to be there. In any conditional statement represented by if P then Q or by if P Q, the P statement is called the antecedent, as I've mentioned earlier, and the Q statement is called the consequent. Occasionally you'll see the word antecedent called hypothesis and the Q called the conclusion. So, identify the antecedent and consequent in the following statements. If our school was this nice, I would go there more than once a week. The antecedent is the P, our school was this nice. The consequent is the Q, I would go there more than once a week. It's just that simple. If you don't get in that plane, you'll regret it. You don't get in that plane is the antecedent. You'll regret it is the consequent. This is just a summary now of what we've said. Sometimes that right pointing arrow is referred to as the arrow notation, but basically otherwise that is just a statement of what we've already said. The conditional statement, if P then Q, can be written using the arrow notation as P with the right pointing arrow, Q. The arrow notation is read if P then Q or P implies Q. And remember, the truth table for the conditional, it's only false if P is true and Q is false. Make sure you get that one right, because at least for me, that's the hardest one to remember. That's the only case where the implication is false. I like to think, sometimes I want to make sure I'm thinking about it right. I'll make up a simple sentence. For instance, if I said, if you need me, I'll be there. Think of it this way. If I said that to you, the only time my statement would be false is if you needed me. That would be like P being true, but I wasn't there. That's like the Q being false. If I said, if you need me, I'll be there, but you needed me and I wasn't there, that would be a false statement. And it's the only time an implication is actually false. There are two more special cases that we need to know. Remember, in the last section we talked about two cases being the two De Morgan's laws. Here are two more special cases that involve the implication. This has to do with taking conditional statements and putting them in an equivalent form. By examining the two truth tables below, we see that not P or Q and P implies Q are the same values. I'm not going through this again, but if we went through the process of doing the truth table for not P or Q, which is the one on the left, and then we did the truth table for P implies Q, which we just did actually, on the right, you notice they have exactly the same truth values. The shaded column on the left truth table is true, false, true, true, and the shaded column on the second truth table is true, false, true, true. So they have exactly the same truth values. That means that those two forms are equivalent to each other because they produce exactly the same truth values. So what I've shown is that the conditional P implies Q is equivalent to the disjunction not P or Q. And we tend to use this symbol in the middle, not an equal sign, but three horizontal bars as being the word equivalent. For our purposes, we're not making much of a distinction, equivalent, equal, but technically that three-bar symbol is equivalent. So P implies Q is equivalent to not P or Q, and I know that because I looked at the truth tables back over on the left and saw that they produce the same truth values. So that's the first of the new special case rules that we need. Let's practice this. If I ask you to write in its equivalent disjunctive form this sentence, if I could play the guitar, I would join the band. Now what they mean by disjunctive form, if you're looking up at the formula, on the right hand side there's an or, and an or is a disjunction. So that's what they're referring to. But anyway, back to the problem. If I could play the guitar, I would join the band. The I could play the guitar is like the P. The I would join the band is like the Q. So I'm taking that statement, which is modeled on the left-hand side of that formula, and changing it to the right-hand side. So right now, I've got the left-hand side of the equation done. I want to change it to the right-hand side of the equation. So I form not P. Well, if P is I could play the guitar, then not P is I could not play the guitar. Or Q, which is I would join the band. So the statement I could not play the guitar or I would join the band is logically equivalent to the statement that I started with, which says if I could play the guitar, I would join the band. So that's a simple example of using this equivalent form of a conditional formula. I'm not going to go through this, but we could show that the negation of a conditional can be written as a conjunction. A conditional can be written as a disjunction, an or. The negation of a conditional can be written as a conjunction, which is an and there's the formula. I derived the other one, or at least I showed that it was true. I'm not going to do that here, but it would be just as easy to do as the other. We just take it for granted. An example, write the negation of the following statement. The statement is if the lines are parallel, then they do not intersect. So the negation of that statement, the lines are parallel is like the P. The if then is the right pointing arrow. They do not intersect is like Q. So forming the left hand side of the statement and changing it into the right hand side of the statement is what they're asking me to do. The P is the lines are parallel. The conjunction is the and not Q would be if Q is they do not intersect, then not Q would be they do intersect. So the negation of the original statement, if the lines are parallel, then they do not intersect, is the lines are parallel and they do intersect. And that's an example of the second of the special formulas that we are introducing right now. Now recall from our earlier discussion that statements of the form P with the double pointing arrow, the double-headed arrow, are called biconditional statements. And the truth table of the biconditional is given here, and the key to remembering it is it's only true if they match. If they're both true, the biconditional is true. If they're both false, the biconditional is true. Otherwise, it's false. And the memory aid is it's true if and only if they match. An example, construct a truth table for the statement P if and only if not Q. And by the way, when you say biconditional, in that double-headed arrow, you say if and only if. So P if and only if not Q. So I'll build my truth table, and as we've done before, adding a preliminary column for that not Q that appears as a piece of the final statement. So I begin my work by taking the Q and changing it to not Q. So I change all the truth values in the Q column to their opposites to get not Q. Then I look and I notice in the final column I have a P on the left of the if and only if symbol. So I'll move those P values from the far left underneath the P. And then on the right side of the biconditional symbol I have the not Q. So I'll move the not Q values underneath. And then I notice that the symbol is the if and only if, the biconditional symbol. And then I've got to remember that the memory aid for biconditional is it's only true if they match. So you're going down and scanning and looking for matches. True if and only if false is not a match, so that's false. True if and only if true is a match, so it's true. False if and only if false is a match, so that's true. And false if and only if true is not a match, so that's false. And there's your truth table. This is again a visual aid to let you see all 5 of the truth values so you can remember these, and underneath them you have the what I call the memory aids. With the negation, you switch the truth values. True becomes false, false becomes true. For an and, it's only true if they're both true. For an or, it's only false if they're both false. For an if then, it's only false if P is true and Q is false. And for the biconditional, the if and only if, it's only true if they match. And then we've added these special cases. From Section 2, we had De Morgan's laws, and from our just immediate discussion, we added 2 more from Section 3.3, and those are the equivalent disjunctive forms of conditional and the negation of a conditional, which puts it into conjunctive form. In other words, disjunctive form is the one with the or, and conjunctive form is the one with the and. So this page summarizes pretty much the basic tools for sections 1, 2, and 3. Let's do another example with the disjunctive form of conditional. What if I ask you to write the conditional in its equivalent disjunctive form? If x is an irrational number, then x is not a terminating decimal. Just proceed as before. The x is an irrational number is the p. X is not a terminating decimal is q. So you want to take that and turn it into the right-hand side of the equation, which says not p. X is not an irrational number. Then the disjunction, which is the or, and then the q, which is x is not a terminating decimal. So you put not p ORed with q, and you get the statement x is not an irrational number or x is not a terminating decimal. Simple enough. If you wanted to add the word either to make it sound a little bit better in English, you could. So if you wanted to make it sound maybe slightly less stilted, you could add the word either in front and say either x is not an irrational number or x is not a terminating decimal, but that's optional. You don't have to do that. Now let's do another example with the negation of a conditional. That changes it into conjunctive form, in other words, to something with an and. What if the statement were, if pigs had wings, pigs could fly? Again, P would be the statement pigs had wings, Q would be the statement pigs could fly, and you want to change it into the right-hand side, which is P and not Q. Well, P is the statement pigs had wings, so you just write that down. The tense doesn't much matter. It might sound better as has or have instead of had, but otherwise that's not really important. But the important part is that you've got to get the and. The conjunctive form produces an and between the statements, and the last statement is the negation of Q. Q is pigs could fly, so not Q would be pigs couldn't fly. Or again, you're not worrying too much about the tense exactly. You just want to make it sound a little better. So you might say something like pigs have wings and pigs can't fly. Not worrying too much about the tense of the verbs. You could change it even to something like this. Pigs have wings and they can't fly. The exact wording is not important. It's the structure that's important and the meaning behind what you said. We talked a little bit earlier in the previous section about the way that WebAssign presents some of these truth tables. So I want to go back to a problem with the conditional and biconditional that presents the table like you'll see it in WebAssign. And here's an example. They're asking you to complete the truth table for this compound statement involving a biconditional. You start off, as you always do, with the simple stuff. You have a Q column, which you want to fill in, so you take the Q values that you already know about and just move them underneath the Q. Then you move over to the not P, so you're going to look at the P column and change all the truth values to their opposites, so the true becomes false, the true becomes false, the false becomes true, and the false becomes true. Then you've got to realize you're working with an and. So the trick for and is that it's only true if they're both true. True false is not both true. False false is not both true. There's a true true, it's true, and the last one is not true true. So there's only one true in that set, and that's the true implies true. Anything else for an and is false. And remember, we talked about this before, once the Q and not P column have been used to produce the and column, those shaded columns are essentially used up. You're only paying attention to that circled column under the and. Then you move over to the other side, and you're going to put the not P in. So you go to the P column and you change all the truth values to their opposites. True becomes false, true becomes false, false becomes true, false becomes true. And notice I've shaded the column under the and because, as I said earlier, the Q and the not P produced that and column in the middle, and so they've been sort of, in some sense, used up. So you don't pay attention to those two columns anymore. You're only interested in the and column on the left side of the if and only if, and the not P column on the right side of the if and only if. And remember, for an if and only if, a biconditional, it's only true if they both match. You notice the very first case, they're both false. That's a match, so it's true. Second, both false, they match, that's true. The third one, both true, they match. The fourth case, false and true, they don't match. So the only false is the very last row. The others are true. And there's the truth table for the compound statement. Let's practice a few more things. Is this true or false? 5 equals 8 if and only if 6 is equal to 4. Remember, this is an if and only if, which is the biconditional. It's only true if they match. If you go back up and look at this statement, 5 equals 8 is false, 6 equals 4 is false, and the if and only if is the double-pointed arrow, or the double-headed arrow, and they do match, so the statement would be true. Another example. This one has a little twist to it. True or false, assuming x and y are real numbers, 2x minus 1 is equal to 11 if and only if x is equal to 6. Now this is still a biconditional, but the best strategy when you have variables in these things is probably to go ahead and solve for x when they're not solved for x. So I would say take that 2x minus 1 is equal to 11 and say, well, add a 1 to both sides and divide by 2, and you end up with x equals 6 if and only if x equals 6. Now, obviously, they're going to match, right? Because you've got the exact same thing on both sides, so how can they not match? It's easy to see that those left and right-hand sides are going to match all the time. If x is equal to 6 on the left, it'll be equal to 6 on the right. If it's not equal to 6 on the left, it will not be equal to 6 on the right. So they will match each time. So even though there's a variable in there, I can see that the left and right-hand sides will match no matter what the value of x is. So the original statement is definitely true. State whether the given biconditional is true or false. Assume that x and y are real numbers. The statement is x squared is equal to 4 if and only if x equal 2. First thing I would notice is that if x squared is equal to 4, there are going to be two solutions. Either x equal 2 because 2 squared is equal to 4, or x equals negative 2 because the quantity negative 2 squared is also equal to 4. So the original statement as written is equivalent to the statement x is equal to 2 or minus 2 if and only if x is equal to 2. Now think about that for a minute. Suppose x is equal to minus 2. If that's the case, then the left side, x equals 2 or minus 2, would be true if x were minus 2. But the right-hand side, x equal 2, would be false if x were equal to negative 2. Recall that a biconditional is true only if the two match. In other words, true if and only if true, or false if and only if false. I've just pointed out a case where you would have true if and only if false. So that means that the biconditional is actually false. Section 3.4 is called the Conditional and Related Statements. We're also doing a short intro to logical fallacies. I want to begin by talking about some equivalent forms of the conditional statement. Every conditional statement can be stated in many equivalent forms. It's not even necessary to state the antecedent before the consequent. In other words, the if part before the then part. For example, the conditional, if I live in Boston, then I must live in Massachusetts, can also be stated as, I must live in Massachusetts if I live in Boston. That's a perfectly equivalent way of stating that conditional. This illustrates the fact that if P, then Q, and Q if P are equivalent ways of writing the same conditional statement. I want to list several logical equivalents to that and sort of give you an example of each. We're not going to go too deep into this, but I do want you to see the breadth. So we start off with if P, then Q. My example sentence is, if you are a citizen of Tuscaloosa, then you are a citizen of Alabama. If P, Q, that leaves out the word then, which is very common in English. So it would be, if you are a citizen of Tuscaloosa, you are a citizen of Alabama. In other words, I'm just leaving out the then. That does not change the basic nature of the sentence, and it's still an equivalent form of the conditional. Another form, Q if P. We talked about that earlier. You are a citizen of Alabama if you are a citizen of Tuscaloosa. That's equivalent to the original conditional. P implies Q. Being a citizen of Tuscaloosa implies that you are a citizen of Alabama. Again, that's equivalent to the original conditional statement. P only if Q. You are a citizen of Tuscaloosa only if you are a citizen of Alabama. Again, logically equivalent to the original. Every P is a Q. The example sentence would be, every citizen of Tuscaloosa is a citizen of Alabama. And Q provided that P. You are a citizen of Alabama provided that you are a citizen of Tuscaloosa. In some of the problems we do, we might need to convert from one of the above statement forms back to its equivalent if-then form. So if you see any of these, you can convert them back to the original first line statement, the if P then Q type. Suppose I ask you to write every parallelogram is a quadrilateral in its equivalent if-then form. What you have to do is look back up at this chart and notice that the next to the last one is every P is a Q. So that tells me that the part about the parallelogram is the P, the part about it being a quadrilateral is a Q. So I can use that and change it back to an if-then form by saying basically if parallelogram then quadrilateral, and then putting in a few words to make the sentence flow. So instead of saying if parallelogram then quadrilateral, I'll add words like if the figure is a parallelogram, then it is a quadrilateral. So it's really just that simple. You're going to use that chart to turn the statement back into if P then Q, and if it's necessary to add a few words to make it sound better grammatically, then you can do that as well. Now let's write today is Friday only if yesterday was Thursday in if P then Q form. Looking back at your chart, you can see that the third one from the bottom is the P only if Q. So that tells you that today is Friday is the P part, which is the antecedent, and yesterday was Thursday is the Q part, which is the consequent. So I can convert it back easily into the if P then Q form by saying simply if today is Friday, then yesterday was Thursday. It's a really very straightforward process. Now let's turn our attention to three statements that are closely related to the conditional: the converse, the inverse, and the contrapositive. Every conditional statement of the form P implies Q has three related statements: the converse, the inverse, and the contrapositive. The converse of the statement P implies Q is the statement Q implies P. You're simply switching the antecedent with the consequent. In other words, you're switching the P and the Q. The inverse negates both the P and the Q, but doesn't switch them. And finally, the contrapositive does both. It switches and negates. So if you start off with the statement P implies Q, to find the converse, you switch the P and the Q to get Q implies P. To get the inverse, you don't switch the P and the Q. Instead, you negate both of them to get not P implies not Q. And to get the contrapositive, you do both. You switch the P and the Q, and you negate both: the converse, the inverse, and the contrapositive. Here's an example. What if I ask you to write the converse, inverse, and contrapositive of the statement, if I get the job, then I will rent the apartment? Remember, the converse switches the P and the Q. In the example, I get the job is the P, I will rent the apartment is the Q, so the converse would switch those, putting the Q in the place of the P, and I would get, if I rent the apartment, then I will get the job. That's the converse of the original statement. How about the inverse? The inverse does not switch, but it negates both. So if P is I get the job, the negation would be I don't get the job. And if Q is I will rent the apartment, the negation will be I will not rent the apartment. So the inverse of the original statement, if I get the job, then I will rent the apartment, is if I do not get the job, then I will not rent the apartment. And finally, the contrapositive does both, switches and negates. So instead of if I get the job, then I will rent the apartment, you switch and negate to get if I do not rent the apartment, then I will not get the job. That's the converse, the inverse, and the contrapositive. Look at the statement, if I drive you to the mall, then you will buy me ice cream. I drive you to the mall is the P. You will buy me ice cream is a Q. This is a conditional of the form P implies Q. How about if you buy me ice cream, then I will drive you to the mall? Notice that you switched the P and the Q. Q implies P then is the converse of the original statement, P implies Q. Do you think this statement and the converse say the same thing? Read both statements. If I drive you to the mall, then you will buy me ice cream. If you buy me ice cream, then I will drive you to the mall. Although it's possible for a statement's inverse to be both true, it turns out that the converse of a true statement is not necessarily true. Go back to the original statement again. If I drive you to the mall, then you will buy me ice cream. How about this statement? If you won't buy me ice cream, then I won't drive you to the mall. Notice that you've negated both P and Q, and you've switched them. That's the contrapositive. Do you think the statement and the contrapositive say the same thing? Read them both. If I drive you to the mall, then you'll buy me ice cream. If you won't buy me ice cream, then I won't drive you to the mall. My guess is you would say these two statements don't necessarily mean the same thing either, but surprisingly, that is not the case. The contrapositive of the statement is true whenever the original statement is true and false whenever the original statement is false. So this is one of the places where your intuition might lead you wrong, but this is the case. A statement and its contrapositive are equivalent, and we'll use this result in later problems. And if you don't believe the truth of this statement, you can verify it yourself. If you build the truth table for P implies Q and then build the truth table for the contrapositive, not Q implies not P, you will see that the truth values are exactly the same. So in summary, a statement is contrapositive or equivalent. A statement is not equivalent to its converse or inverse. Let's try some examples. Are the statements equivalent? If you go, then I stay, and if I don't stay, then you won't go. If you think of this in the symbolic form, if you go, then I stay is of the form P implies Q. If I don't stay, then you won't go is of the form not Q implies not P, which is the contrapositive of the original statement. So yes, these are contrapositive, so they are equivalent. How about this one? Are these statements equivalent? If you go, then I stay, and if I stay, then you go. Well, if you think of that first statement of being of the form P implies Q, the second statement is of the form Q implies P. These are converses. Converses are not equivalent to each other. So the answer is no. If the statements are not converses, inverses, or contrapositives, if you ever come up with that case, you just have to do the truth tables to find out. But if you do get a statement that's contrapositive, you can immediately say they're equivalent. We're going to include a short intro to the topic of logical fallacies. So first of all, what is a logical fallacy? Basically, it's an argument that's not valid. More specifically, a logical fallacy is an argument with an error in logical reasoning. Logical fallacies are like landmines. They are easy to overlook until you find them the hard way. One of the most important parts of college life and life in general is serious discussion and discourse, which, one hopes, leads to reasoned arguments and debate. Unfortunately, argument and debate almost inevitably lead to the use of flawed reasoning and rhetorical errors. Many of these errors are considered to be logical fallacies. There are way too many logical fallacies to attempt to introduce them all here, but we will discuss a few of the common ones. I'll just list them. We're going to go through them one by one. One is called the causal or sometimes false cause fallacy. There's one called the red herring fallacy, the straw man fallacy, the slippery slope fallacy, the false dichotomy fallacy, the ad hominem fallacy, the appeal to authority fallacy, the circular reasoning fallacy, the confirmation bias fallacy. Let's talk about these one at a time, just briefly. Start with the causal or false cause fallacy. This fallacy establishes a false cause-effect relationship. Morty says, "That drink you gave me must really be a love potion." Rick says, "Why do you say that, Morty?" Morty says, "Jessica never noticed me until I drank the potion, and now she says she loves me." What makes this a causal fallacy? Think about it. Morty made the unfounded claim that Jessica falling in love with him was caused by the potion. There's no supporting evidence. It's just something he said. The red herring fallacy. This fallacy brings something into the argument to distract from the original topic. Some people call this type of argument a smokescreen. Marge says, "It's all my fault that Bart turned out this way." Homer, "Well, you always did let Bart wear a bathing suit instead of underwear, so it is your fault." What makes this a red herring fallacy? Homer brought up a totally irrelevant fact and used it to conclude that it was Marge's fault. The straw man fallacy. This fallacy introduces a weak case or a misrepresentation and argues against that instead of the real point of contention. For example, Alex says, "Bicycle infrastructure should be expanded because cycling is sustainable transportation." The mayor says, "I disagree because cyclists run red lights and endanger pedestrians." What makes this a straw man fallacy? The mayor brings up a much weaker case, just looking at a couple of negative aspects, in order to switch the argument over to that instead of debating the original, much broader topic of infrastructure. The slippery slope fallacy. This fallacy introduces an argument that taking a minor action will lead to major and sometimes ludicrous consequences. Lois says, "Peter, please, I saw an ad for a used car that would be perfect." Peter says, "Oh no, Lois, a guy at work bought a car out of the paper, and 10 years later, bam, herpes." What makes this a slippery slope fallacy? Peter claims that some minor action, like using an ad to buy a used car, could lead to the rather ludicrous outcome of getting herpes. The false dichotomy fallacy. This fallacy occurs when someone presents an argument as if there are only two choices. Alice says, "I love cats." Bob says, "So you hate dogs?" What makes this a false dichotomy fallacy? Bob makes it seem as though there are only two choices. If you like cats, then you hate dogs. And of course, that is not the case. The ad hominem fallacy. This fallacy replaces legitimate arguments with personal attacks. Eddie says, "I'd like to tell you about my plans for improving education in our city." Mark says, "Why should we listen to Eddie? His own son flunked out of high school." What makes this an ad hominem fallacy? Instead of addressing Eddie's ideas for improving education, Mark instead resorted to personal attacks. The appeal to authority fallacy. This fallacy claims that you should believe or agree with something just because a person who is said to be an authority on the topic tells you to. Me, "What cereal should I eat?" You, "Whole grain Wheaties, that's what Michael Jordan eats." What makes this an appeal to authority fallacy? It's because you told me to eat whole grain Wheaties because you think of Michael Jordan as an authority on what to eat because he's an amazing athlete who must know all about smart eating choices. The circular reasoning fallacy. This fallacy assumes the premise of the argument is true in order to prove that it's true. It's like arguing in a circle. Beth says, "I'm athletic because I run." Sam says, "Well, what made you start running?" Beth, "Being athletic." What makes this a circular reasoning fallacy? Because Beth is basically saying that she is athletic because she is athletic. The confirmation bias fallacy. This fallacy occurs when someone is more inclined to accept a statement or idea based on preconceived ideas which may or may not have a solid basis in fact. Jackson says, "I'll read your horoscope if you believe in that sort of stuff." Allison says, "Yes, I want to know what my horoscope says. My last horoscope said that I would meet someone new and I met you." What makes this a confirmation bias fallacy? Because Allison believes that her horoscope has been right in the past, she is more likely to think that her new horoscope will be accurate. This probably makes her more likely to interpret events more favorably for her new horoscope and look hard for things to prove it correct. Just to look at them all at once, we have the causal fallacy, the red herring fallacy, the straw man fallacy, the slippery slope fallacy, the false dichotomy fallacy, the ad hominem fallacy, the appeal to authority fallacy, the circular reasoning fallacy, and the confirmation bias fallacy. We're not going into huge detail on this, but when you see a scenario, you should be able to identify which one of these fallacies best describes it.